Hi everyone, welcome to my presentation. My name is Tim Liu. I'm currently a postdoctoral researcher at UC Berkeley and Lawrence Berkeley National Lab. And I've been doing research in particle physics for over 3 years. And I got my PhD from Princeton roughly 3 years ago. And today I want to tell you a little bit a story on how I got to where I am, how I become a researcher in particle physics. And this journey took me roughly 10 years. It all began at high school. I was just really curious into science. And I remember it was chemistry class, roughly when I was a junior in high school. And in chemistry class, you learn about things like chemicals, elements, particles, and whatnot. But I just sort of asked this question: what exactly are things made of, right? So we live on this beautiful blue planet. There are oceans in it. There are people. There are buildings. You look at the table. There's wood. Wood is made of molecules. And your teacher may tell you that, oh, these molecules are made of atoms and whatnot. And the atoms are made up of neutrons and protons and electrons. But then one question just pops up. Well, does it ever stop, right? What are these particles made of? And I got really curious, but I couldn't find an answer. The textbook wasn't able to offer me any information. Then I just really want to know the answer. And I look online, I search all over the internet, and indeed, to my surprise, there's an answer. In fact, science has already learned a lot more about our fundamental world. So I come across this really excellent website. I would encourage all of you to visit. It's more than 10 years old, in fact. And it's a little website called the Particle Adventure. And they have these really sort of nice animation and pretty pictures. And in fact, we know that our world is made of just a few types of what we know as fundamental particles, right? And they come with some pretty eccentric and interesting names. So first of all, we have 6 types of quarks and particles that are similar to electrons, and things like force carriers, like photons, gluons, and the latest addition, the Higgs Boson, that you might have heard of. And this is just super fascinating, right? When I was a young student, like it's like the new periodic table of everything, right? But so I found out this fact. I was amazed, but then a mystery is slowly unfolding then. Well, the first mystery is that I found out was, well, most of the things we know exist, like you, me, and the planet, is actually only made of a few of these particles, right? Things like the protons and neutrons are made of up and down quarks. And chemical reactions mainly deal with interaction with electrons. And the things that we typically deal with in our everyday life is electricity and whatnot. It's mediated by force carriers with photons and gluons that binds the nucleus together. So what happens to the remaining piece, right? It seems to me that you know, we perhaps we really don't understand what is the bigger picture that governs these particles, right? So, but anyway, I want to answer this. This mystery comes up, and I want to learn more about it. So after high school, I was really interested in physics, and I went to Rutgers University to pursue an undergraduate degree in physics. And slowly, and I would learn more and more about physics, but it would turn out that it would take me around 10 years to really learn about all the complicated mathematics that govern the interactions with these particles. But today I want to share with you just 10 years of physics. If you were to condense it into one line, what would it be? And the answer it's actually possible. Well, that's the first thing. And the interaction that govern all these particles and fundamental physics is actually remarkably simple, and it can actually be summarized. So there are two big players, right? So the first player is particles, right? Like I told you before. And these particles can roughly be categorized into different groups. They are the matter particles that made up of stuff, I guess. And they're also the force carrier that bind these matter particles together. So that's the first player, right? And the second player is their interactions, right? So their interactions are actually very, very simple. It's very similar to chemistry that one might learn, right? So these are summarized by different sort of what we call interactions, which are really just sort of chemical rules, right? It tells you that one particle can be converted into other types of particles. You can have one particle turning into two particles and vice versa. And if you just take particles and you take their interactions together and you just put them together and combine with mathematics, then the remarkable thing is you are able to describe all kinds of objects. Like you're able to describe atoms, you're able to describe the structure of the nucleus, and things that are seemingly vastly different can be described in this one single framework. And to me, it's extremely remarkable. And during my journey, of course, this theoretical understanding is not enough. This is science after all, right? We can't just be satisfied by equations and formula. We have to test these out. And indeed, we have some of the most amazing experiments on Earth currently in operation trying to verify these laws of nature. And some of you might know already, that experiment is called the Large Hadron Collider in Switzerland. And this is sort of a top-down picture in Geneva. The size of it, the width of this is roughly comparable to the width of San Francisco. So this is very large. It's a huge collision ring. So what they do is they take protons and they smash them against each other and see what comes out, right? And in these interactions, what we're trying to do is we can literally recreate these interactions. We can isolate these interactions and show that this theory works, right? And so during my undergraduate career, I really want to learn more. I want to be a scientist, and as a scientist, I have to learn the theory and the experiment. So in the summer of my junior year in college, I was lucky enough to be selected to join one of the summer research program offered by University of Michigan. And I actually went to Switzerland for during the summer to join forces with scientists to understand how this machine works and how to interpret data. And so this is me at the CMS, one of the experiment at LHC, and I went on a tour there. It's an amazing machinery. It's a huge detector. It's like 3-story tall. It's the biggest, most powerful particle collider in the world. And it just blew my mind at that point, right? I've never seen something like this. And in addition to that, the numbers are mind-boggling. Like the stats sort of for the detector. And as a science enthusiast and a student, it just blows my mind. So the temperature of the Large Hadron Collider can reach almost a trillion degree. This is like a million hotter than the surface of the sun, right? This is one of the hottest places in the entire universe, right? And at the same time, it's also one of the coldest, right? In order to have all these electronics working together, they have to cool it. They have to use superconducting magnets. They have to cool it below 3 Kelvin. It's colder than the outer space, right? So these are extreme conditions, and yet we're able to measure things down to the size 1,000 times the width of an atom. It's amazing. It's an amazing achievement, right? And incredibly, all of these actually work and came together. And as I remember, at around 2012, I was still a graduate student. Something amazing happened. We have the discovery of the Higgs boson. And so at that point, I was a graduate student at Princeton already. I've been studying physics for many years now and sort of understood the laws of nature. And I sort of distinctly remembering that day. So they were having an announcement at CERN in Switzerland. So there's some time zone difference. So it was around 3 a.m. at East Coast time. I was at Princeton. I remember everyone was excited. We got emails from professors, oh, we're going to have a party around 3 a.m. But, well, I didn't want to come to school, but I stayed at home. I set my alarm around 2:50 a.m., woke up, and I just go online and saw the broadcast. And I see, so this is sort of what it looks like. You just have a room filled with scientists, physicists, looking at a PowerPoint presentation, right? So how exactly did we discover the Higgs boson? Well, it may sort of sound intimidating and very complicated, but the idea is actually very simple, right? So let's zoom in a bit on what exactly does the Higgs boson look like, right? Well, a Higgs boson, when it's produced, it doesn't live for very long. It decays almost immediately. So when we make one of these particles, we can't really catch it while it's still around. The only thing we can find is the remnant of its decay products. So this is an actual data event, right, that Atlas gathered, which could be a Higgs boson in action. So let's dissect this picture a little bit. So you can imagine protons and protons coming together, right? And they collide right here. So these are enormous detectors, right? Although the beamline, the size of this beamline, it's around like 1 meter long. It's roughly the size of this, right? So it's not very large, but the outer detector can extend to very, very large. So this is only a small part of the detector, right? So protons comes in, it might have created a Higgs boson, we don't know, right? Everything's random. And out comes a lot of particles, right? So most of these particles, you see these lines these lines basically attract left behind by the particles. Most of them are just remnants of the proton, because after all, you are breaking down the proton. Proton is a very complicated object, and so there are a lot of remnants coming off. We don't care about those, right? The interesting particle are these particles of light, or photons, so to speak. So our theory predicts that the Higgs boson can decay to 2 particles of light, 2 photons. And we see 2 energy deposits in these calorimeter. And these are the events, these are one kind of events that we're looking for. And once we grab these events, we can compute what's known as the invariant mass, or just the mass of the particle. And if we have a Higgs boson, the mass will be at a very specific value, versus if this is just coming from noise or background, the mass would basically be scrambled and just random, right? And now I want to show you the actual data that led to the discovery, right? So these plots are literally what the scientists use to claim this discovery. So the x-axis is just the mass of the particles, the mass of the Higgs that you compute. Here, it's the mass for the particles of light. So you see that, and this is a slightly different decay product for leptons, but it's very similar. So basically what you do is, each time you see an event, you just compute the mass, and you just put a histogram, basically. These are just histograms of how many events you see, right? And slowly and surely, as you gather more and more data, you see the red here is the noise. And here you see that most of it is noise. But one interesting feature always remains, is that there's a little spike here, the signal, at 125 GeV. That's how we know the mass of the Higgs, right? And in two separate instances, we see a little signal here. And that's what made the discovery. And this is literally, making these histograms are literally just how physicists discover particles, right? So when you get right down to it, it's just, at the end of the day, it's just like you're just doing a counting experiment, right? So then, after this remarkable discovery of the Higgs boson, what's next, right? So science doesn't just stop there, right? In fact, most physicists would agree that this is just the beginning. The Higgs boson was actually the last particle that was predicted to exist from the standard theory that we call the standard model. But is there something more, right? So could this be it? Could it be as simple as just the standard theory? Well, we know for a fact that it's not just the standard theory. There has to be something more. And this leads to some of the deepest puzzle in particle physics. And the thing that's missing, one of the most important things that's missing is gravity, right? So why is gravity so interesting? Well, in our everyday lives, we experience gravity, right? We know gravity exists, right? In fact, the fact that I'm standing on Earth is a proof that we have gravity, right? But the strange thing is, in particle physics, we actually don't care about gravity. Well, why, you might ask? It's because gravity is so weak. In fact, gravity is like trillions and trillions of times weaker than every other interactions. And from a particle physics point of view, we don't really know why. Why is particle so weak? Well, you might ask, well, I don't think gravity is really weak. I'm standing here on Earth. We're all trapped on the surface of the Earth. Why is it so weak? Well, from a particle physics perspective, well, the reason why you're standing on Earth is because the entire Earth, the entirety of the Earth, the core, the 6,000 miles of radius of rock, it's sucking you down to the Earth, right? So with all this attraction, you're not crashing to the center of the Earth, right? Why? It's because a measly few electrons on the ground, it's stopping you. So that tells you how much weaker gravity is as compared to other fundamental forces. And this is sort of a big conundrum, right? So we have all these forces, all the other forces are sort of comparable in strength. Why is gravity so weak, right? And we don't really know why. But this question is actually not just sort of a philosophical question, right? We can wonder, oh, why is it so weak? Why does it matter? Well, it matters because if gravity is not so weak, the universe will look drastically different. For example, if gravity is a lot stronger, then all the particles we know and love that will simply collapse into black holes. Then there will be nothing interesting left. There will be no planets, no galaxies, and most of all, there will be no humans to explore this wonderful world. So it's an extremely important question. Are there reasons why gravity is so weak? So that's one question we might ask. And the answer, there are multiple hypotheses that we might test. Maybe there's extra dimension. Maybe gravity, it's only weak because we're confined to a smaller dimension than nature permits. Maybe there are other new particles that could explain why it's so weak. There are many theories proposed. Supersymmetry is one of them. So we're still waiting for the answer, right? And there's another equally important mystery, is that actually most of the mass we see in the universe, most of the mass in the universe is missing. We cannot see them. So how do we know this? Well, we have a lot of data on looking at galaxies and the way stars move around galaxies. And you know, if I just give you a picture of a galaxy, it's like a disk. You might imagine that the farther away I'm from the center of the galaxy, the slower I would move, right? Just because I'm sort of further out, that I'll move slower. But that's actually not what we found. In fact, if you look at this graph, it's called the rotation curve of a galaxy. And this is the radius. It's roughly how far away from the center of the galaxy, right? So you see that around here, the further away you go, you're actually moving faster. That's not what we expect. How could that be? The further away, the faster you're moving, right? There must be something missing, right? And indeed, what that something we call dark matter, right? So far we have no evidence of what dark matter is, other than the fact that it has to be there. Without dark matter, there will be no galaxies. There will be no planets. We wouldn't be able to exist, right? So these two extremely important questions that are deeply connected to our existence are still unanswered. So I would say this is only the beginning, right? And and every day I struggle with these two questions. And as a postdoc researcher, I'm just thinking of solutions to these problems and maybe ways to sort of take a small crack at these problems. And I would say this is really the most amazing part about science. It's that we can contemplate about these mysteries and maybe come up with a solution. And with that, I want to show you this amazing video in the background, right? So this video is a simulation of what our universe looks like, right? So given that dark matter is the dominant form of matter in our universe, it dominates normal matter 5-to-1 in terms of mass and energy. So the structure of the universe is also dictated by it, right? Because it's so much, the total mass is so much more. So what people have done is, well, let's take a bunch of dark matter, give them gravity, and see what a supercomputer will tell us, what they will look like, right? And if you run the simulation for about 13 billion years, the age of our universe, this is roughly what you will see, right? So these are marvelous simulations. So the size of a galaxy is really small. It's about 1,000th the size of one of these specks, right? But we're able to extrapolate roughly what the universe looks like. You can see these amazing structures of where bright stars indicate dense patches of the universe. There are dense patches that we might expect to see. There should be dense patches, dense galaxies, and we are just one tiny speck in this little picture. And that to me is amazing. So if you're interested in this journey of figuring it out and trying and come up with interesting questions and see what you can do to help us solve this mystery, please go to this website, and you're welcome to send me email for any questions that you might have. So, thank you.